friends, I welcome you all in this session. As you are aware, in previous session we were discussing about the assumptions of ANOVA, and one of the assumptions was the equality of variances of populations from where we take samples, and for that we applied Levin's test. And we have seen that in Levin's test the null hypothesis was that all variances were equal and alternative was they were not equal. So, we did not reject the hypothesis, it means we concluded that the all variances were same, and once that hypothesis is not rejected, means null hypothesis is not rejected, we are now in a position to solve a question on ANOVA, right. So, in today's class we are going to talk about the second type of experimental research design. It is called randomized block design. As you are aware, the first type of design was completely randomized design, where we study the effect of treatments on dependent variable. So, what we do in randomized block design is it is very similar to completely randomized block design, which in fact focuses on one independent variable, but here in randomized block design it includes one more variable, and this variable is referred as blocking variable. So, this blocking variable can be used for controlling the confounding or concomitant variables. Now, what are these confounding or concomitant variables? So, these are the variables which affect the output. As we know that the dependent variable gets affected by independent variable, but there are some variables which affect the dependent variable as well apart from independent variable. So, these variables are actually not being controlled by the researcher in the experiment. So, we need to control them in one way or the other. So, blocking variable helps us in controlling confounding variables. We will take examples of these variables, confounding variables. So, we have seen an example wherein we just tested the effect of temperature on tensile strength of metal using one way ANOVA, and that was a case where we used completely randomized design, right. Now, if you look at this example, then you will find that the tensile strength depends on several other factors, it is not only on temperature. For example, let us say you have got different suppliers of raw materials, you have got different shifts, you have got different operators on the machine, you have got different weather conditions, you have got different humidity levels and so on. So, there are several confounding variables which affect the tensile strength, which we have not controlled in the first part of experimental design, which was completely randomized design, right. So, you can have several such confounding variables which would be affecting dependent variable apart from independent variable, right. These are some of the examples of blocking or the confounding variables, and we need to block all these. Suppose if we block, let us say worker, when I say worker means the skill set a worker possesses. So, if we take worker and we block this skill set, so we will have workers of different skill set and different temperatures, and then we will measure tensile strength. Or we can check the tensile strength of metal when the metal is being, or let us say the operation is being done in different shifts and at different temperature levels. So, this would become in that case a blocking variable, right. So, this is the question what we have seen, wherein there were 5 different temperature conditions and this was the tensile strength. So, we checked this whether the tensile strength has got or whether the temperature has got any effect on tensile strength. So, this is what we have seen in one way ANOVA. So, generally what we do in any experiment, we do not control confounding variables, but actually they affect the dependent variable, in this example tensile strength, and these are some of the confounding variables, right. So, one way to control these variables is to include them in the experiment. So, the randomized block design has the capability of adding one of these variables into the analysis as blocking variables. So, we can use randomized block design wherein we would be using one of these confounding variables as a blocking variable. So, what is a blocking variable? Is a variable that the researcher wants to control, but is not the treatment variable of interest. Okay. So, though we will focus only on treatment independent variable, but we will have a blocking variable as well. So, in reality what happens whenever you perform any experiment, you know that the independent variable might affect dependent variable and there would be several confounding variables. So, you will try to control those confounding variables. So, as I said, blocking is one of the methods of controlling confounding variables. So, you can have any confounding variable, let us say machine or worker or shift or let us say humidity or any other confounding variable. So, that confounding variable would be designated as blocking variable. Now, in other experiments, some other possible variables that might be used as blocking variables, such as again the gender of the worker, the educational qualification of the worker, the age of the worker, intelligence of the subject. So, there can be n number of confounding variables. So, this is how the partitioning of total sum of squares happens. So, this is column sum of square and this is error sum of square, which is again summation of this row sum of square and this is error sum of squares, right. So, if you calculate these two, then you can easily find out sum of total squares. This is how the layout of the randomized block design looks like. So, you have got single independent variable. So, over here just one independent variable with different treatment levels and there is one blocking variable, right. And these are different cells wherein you would be having different observations and that would be nothing but dependent variable. So, here at each of these intersections we are taking just one measurement. So, you need to frame null and alternative hypothesis. So, null hypothesis is that the means of these columns are same, right. So, mu 1, mu 2 to mu 3 and all other means are same, and alternative is they are not same, right, they are different from each other. Similarly, for blocking effect, at least one of the blocking means is different from others. It means this mean, right, mean of these values. So, you have got column mean over here, let us say x bar, here you have got, let us say call it y bar for simplicity, right. So, mean of row. So, we are saying that all these means of rows are same, and alternative is that they are not same, right. But again our main focus is on the effect of independent variables on dependent variable. Our main focus is not on whether these block means are same or these row means are same. Main focus is on whether these column means are same or not, right. So, this is how you can calculate column sum of square, row sum of square, error sum of square, and then total sum of squares. So, you can have different, let us say treatment levels, you can have block groups, number of treatment levels, C, n is number of observations in each treatment level. These are individual observations, treatment mean, block mean, grand mean, and total number of observations. So, you need to calculate something called F value. So, F for you will be calculating two F values for treatment as well as for blocks, right. So, let us take an example of randomized block design. So, let us take an example where there is a company which has developed a new tire, and the company wants to test or want to check tread wear of on these tires, how these tread wears occur on tires with a varying speed of the vehicle, right. So, the company has set up an experiment where independent variable is speed and the dependent variable is nothing but this tread wear, right. So, how speed is affecting tread wear? So, this is your dependent variable dV. So, there were three treatment levels. So, in fact an experiment was set up and the three speeds were chosen, 20 miles per hour, 40 miles per hour and 60 miles per hour. So, these are three different treatment levels of independent variable which is speed, right. Now, we know that the tread wear also depends on several other factors, not only on speed. For example, let us say who were the suppliers of raw material for which tire was made, who made the tires, in which shift the tires were made, what was the temperature conditions when those tires were made, what was the humidity condition, what was the, let us say, educational level of the workers, and so on. So, in this experiment we have decided to block just one variable, and that was raw material supply, right. So, in this experiment there were 5 raw material suppliers, and the company manufactured tire from those raw materials which they received from 5 suppliers. So, we will say that the blocking variable is supplier. So, what we have done in this experiment, what the experimenters have done is that they took 3 tires from each supplier. So, total 15 tires were randomly selected for the study. So, 3 tires from each of the suppliers. So, total 15 tires. Each of the three was assigned to be tested under different speed conditions. So, the data on tire wear in terms of units of 10,000 miles are given in next slide. So, let us say there are 5 suppliers and 3 speeds, right, slow, medium and fast speed. So, this is the tread wear when experiment was performed on tire manufactured from raw material supplied by supplier 1 and the speed was slow. What is this? The tread wear, the measurement or the dependent variable tread wear when the speed was fast and the tire was made from raw material supplied by supplier number 5. So, we have to find out, is there any significant difference in these means. So, that is the question, right. So, this is, so you can have treatment null hypothesis for treatment, right, that all, let us say mu 1, mu 2 and mu 3, all these column means are same, right, and they are not same is alternative hypothesis, right. So, you need to test this hypothesis at 99% significance level or alpha is equal to 0.01, right. So, we know that there are 3 groups, these 3 levels, there are 5 suppliers and total 15 observations. So, you need to calculate column sum of squares, row sum of squares and error sum of squares. So, if we know all these 3, we can calculate total sum of square, right, which is this 5.176, right. Now, let us find out what is the value of f, which is 97.45. This is output from this is ANOVA table, right, ANOVA output table. So, f is 97.45, it is much higher than value 1, right. So, your distribution would look like this, right. So, this is your rejection region, right, and this value is let us say 97.45 and this is your critical value actually, right. So, this critical value is in fact is to be found from table, right, it is 8.65. So, we will reject null hypothesis. It means that at these 3 different steps tread wear are different, mean number of tread wear are different, right. So, we have rejected null hypothesis, right. So, there is a significant difference in tread wear for cars driven at different speed, that is our conclusion, and this is the Minitab output where p values are less than alpha, right, 0.01 was the alpha. So, here both these p values. So, we will say that there is a significant difference in means of tread wear of different suppliers, right, as well as different speed. We will go back to our question. So, the mean, these means they are also significantly different, that is why you are getting 2 p values or 2 f values in ANOVA table, right. Just see these 2 f values. Okay. So, we will say that there is a significant difference in tread wear as far as speeds are concerned and as far as the suppliers are concerned, right. So, this is the output from Excel, right, same answer, just see this p values for let us say supplier is 0, this is supplier means row, right. So, just see this is as good as 0, then for speed which is column, right, this is for column, right, p value is again approximately 0, f values these are critical values of f, right. So, which are these are critical values and these are actual values, right. So, you can see that these f values are greater than critical values. So, you need to reject null hypothesis. Okay. So, we will work out this question using Minitab, and let us see whether we get the same answer or not. So, you have got suppliers and speed, and this is Tradeware, right. So, there are 5 suppliers, right. So, we can write supplier 1, supplier 2, supplier 3, supplier 4 and supplier 5. And if you look at, in fact, this is to be repeated several times. Because there are total 15 observations. So, 15. Let us look at speed. So, the first is slow, right, then medium, and then okay, you can have in fact 5 slow, 5 medium and 5 fast, right, and then next fast. Yeah, right. So, now you need to enter Tradeware values, right. So, supplier 1 speed slow, what was the Tradeware? 3.7, supplier 2 speed slow 3.4, supplier 3 speed slow 3.5. Similarly, you are supposed to write for supplier 5 when speed is slow. Now, after entering all these points, we need to enter data for all these suppliers when speed is medium, right, and after that you need to enter data for all 5 suppliers when speed is fast. So, you have got this data entry done. Now, we will go to stat, ANOVA, go to general linear model. This is the point you need to remember, right. General linear model, fit general linear model, right. So, you have got response is nothing but your dependent variable, right, and factors are your independent variables, right. So, these are factors, right. So, we will go to let us say options to check on the significance level. So, this is to be tested at I think what percentage, at what significance level? It was 99% significance level, right. Okay. Right, we will get the answer now. So, this is the output. We will look at the this ANOVA table first. Just look at this. For supplier it is 0, p values, for speed also 0, right. So, we will reject null hypothesis because these two are p values is less than alpha for supplier as well as for speed, right, and these are f values. Now, if you look at, if you go downward, just let us see what are other things there in the output. Okay. In fact, the other things are not of use. So, you just look at the f values and p values, right. So, you are rejecting null hypothesis. Okay. So, this is how you should solve a question. We will move on to second question. Let us look at one more example. Suppose a National Travel Association studied the cost of premium unleaded gasoline in United States during summers of 2010. So, from the experience, the director of the association believes that there was a significant difference in average cost of the gasoline among urban areas in different parts of the country. So, he thinks that the price of the gasoline is different in different parts of the country. So, to test this belief, they placed a random call to gasoline stations in 5 different cities. In addition, the researchers they realized that the brand of gasoline might make a difference in price. So, their independent variable is whether there is difference in cost of gasoline in different parts of the country, or these 5 cities of the country, and they were they knew that the brand also affected price. So, they set up an experiment and they got this particular data. So, this is how they collected data. They randomly called the gasoline stations, and there were 5 different brands of gasolines across 6 different, there were 6 brands of gasolines across 5 cities, right. So, in all they collected data from 30 gasoline stations, wherein they chose one brand and one city, right. So, that is how they chose total. They collected data from 30 different gasoline stations. So, each station operator was asked to report the current cost of the gasoline, right. So, the data are shown in the next slide. So, they test these data by using a randomized block design analysis to determine whether there is a significant difference in average cost of the gasoline by city. So, there are 5 cities and gasoline prices were noted in all those cities for 6 brands, right. So, we need to test this hypothesis at 99% significance level, right. So, this is the data, right. So, these are different regions, Miami, Philadelphia and so on, right, Oakland. These are 6 different brands of gasoline, right. So, this is the price of brand A in Miami city, this is the price of brand F in Oakland, right. So, we need to test whether these means are same or not, right. So, let us say x m, right, x bar m, x bar p for Philadelphia, right, x bar o, right. So, all these means are same or not. So, null hypothesis is they are same, right, and alternative hypothesis they are not same, right. Similarly, the second null hypothesis whether these means are same or not, the row means are same or not. There are 6 row means, right. So, you can solve this example similar to what we solved the earlier example. So, you have got null hypothesis that all these 5 column means are same, then for blocks or for blocking variable all these 6 row means are same, right. So, we need to test this hypothesis at 0.01 significance level, right. So, after calculating the column sum of square, row sum of square and let us say error sum of square, you can find out total sum of square, and this is your f value. So, f is you have to compare this f value with the critical value, right. Okay. So, let us find out answer to this question, and this is our Minitab output. So, let us look at what was the what was the significance level. It was 0.01, right. So, 0.01 alpha is 0.01, right, 0.01. So, p value is this. So, we will reject null hypothesis this. It means city wise there is a significant difference in price, but brand wise there is no significant difference, because you will not reject null hypothesis here, and here you will reject null hypothesis. So, we will find out solution to this particular question. In fact, this is an output from Excel, this ANOVA table. So, let us solve this question using Minitab. So, we can go for data entry first of all. So, you can have a new file. So, we will enter data for all these 30 observations. So, you have got brand, city and price. Price is nothing but your response variable or dependent variable, right. So, brand A, B, C, D, E and then F, right. So, you can copy all these. So, this is you will have 30 observations, right. And one more time, right. So, this is you have got observation for the entry for brands, and you have got cities, right. So, if you want, let it be C1, C2, C3, C4, C5, right, rather than writing. Okay. Philadelphia, okay, let it be PHILA, right. So, up to 12, right. Then next is the next city. So, up to 18, this will go up to 18. Then next city, up to 24, and finally Auckland, right. And then you can write prices. So, you can just copy and paste it up to point number 30, right, or serial number 30. Let us write prices over here. So, brand A Miami 3.47, then brand B first city, brand C, brand D, brand E, and last brand is F brand, right. So, there are total 6 brands. So, these are the prices of 6 brands in Miami city. Then price of these 6 brands in Philadelphia. So, this is brand A, the third city 3.38, then 3.42, brand C, then D, E and F, right. Now, we are left with 2 more cities, right, for all these 6 brands. So, once you are done with this data entry, you are supposed to look at the ANOVA table, and you need to look at p value specifically, because there you are deciding whether you are rejecting or not rejecting null hypothesis. So, this is how you should go for data entry, and then go to stat, go to ANOVA, it is general linear model, fit general linear model. So, your price is now response variable, and the factors are brand and city, right. Select. You need to look at the significance level, it is correct, it is 0.99 or 99%. So, we will click at OK. So, we will go to ANOVA table, and see what are the values of P, right. So, look at this same answer, right, what I had shown in slide. Just I will show you once again. Yeah, just see, it is 0.667 and 0, right, 0.667 and 0, right. So, you will reject null hypothesis and you will say that there is a significant difference in price so far as cities are concerned, but there is no effect or there is no difference in price as far as brands are concerned. So, with this let me complete today's session. In next session we will have some more examples. Thank you.